How about now? I see I'm lagging behind a few minutes. How about now? There we go. I can hear me, so you can hear me too. Okay. Yeah. So, I think the approach I had before was correct. Was your AirPods accidentally connecting? Well, I wasn't hearing myself on stream either, so. So what is it? So we suppose, to the contrary, that there's a non-trivial linear combination here. And we multiply by I, like before. What am I doing? Plus Zij. And as before, we argued that Z can't be 0. If Z was 0, everything else would be 0. So we can rearrange the final solution of the quaternion question. True, Boris. Yeah, true. It is ominous. Let's see. The other terms will be negative. So we got minus Z inverse xi. Well, I should put minus a Z inverse y minus x Z inverse I plus a Z inverse j. Sorry, I should have poured that coffee into the microphone. Got that ASMR going. Not into the microphone, but you know what I mean. Right, so like before, we get some equations here. But I realized that we can actually get more info. We can rearrange this to get some more information here. So Z is AZ inverse. Do I know the idea of the proof of equivalence of both K-algebra definitions? I don't know. What two definitions are you thinking of? I mean, I don't have it memorized, but I do think it would be very straightforward to prove. But I don't know which definitions you're thinking of. Oh, wait a second. No, maybe I did this wrong. I woke up and I jotted something down on a piece of paper. I had a flash of inspiration, and now I'm wondering if I did that correctly. Okay, multiply by I. That's all correct. Rearrange. Let's see. Should be AJ minus XI minus AY, and then multiply by Z inverse. Yeah, okay, so that's all right. That is all right. Hang on. So it should be X is minus a Z inverse Y. Yeah, and Y is minus XZ inverse, and Z is a Z inverse. Oh, somehow I had convinced myself that Z was supposed to be equal to A, but now I'm starting to doubt that. Okay, but maybe this still works. Maybe I was wrong. Maybe we won't actually find the solution today. Oh Lord. Well, we do know that AZ inverse is Z, so we have that X is minus ZY. And so I suppose these two equations are really telling us the same thing. And we know that Z squared is A. What does that tell us? Well, so that tells us that A is a root, though. That tells us that A... that tells us that A is a square in the field. But this is a contradiction because remember that we specifically chose A to live outside of here. So maybe we're already done? Does that already do it? Yeah, I guess it does. Maybe someone watching this later will find a flaw, but I think that's it. Okay, well, the homomorphism from ZA definition and the vector space style definition. Well, if we go look up the precise definitions, maybe we can solve it. Quaternion saga is over. Yeah, I think we solved it. So this is the vector space definition. What's the other definition? Defined by ring homomorphism from K into the center. Yeah. So yeah, I don't think there's a lot to say about it, right? Well, I think it needs to be in the center of A, Nicholas. Because you want it to commute with the other things. So I think specifically the hom has to lie in the center. Yeah. But certainly this turns the algebra into a vector space, right? Because I mean, if you had a hom in here, then what's your scalar multiplication is just going to be fx times a. So I don't know. I think one direction is clear, right? Like, well, you do algebraic geometry, so ring equals commutative ring in your world. Ah, I see. Right. Yeah, it is not the case in my world. I do algebraic geometry. Maybe not. I mean, I'm not an algebraic geometer. Otherwise, I'd probably agree with you. But then there's non-commutative geometry. But then can you really call those people algebraic geometry? I don't know. Yeah. So I think, I mean, Daisen, you can tell me otherwise, but I think one direction here is clear. The other direction, where we start with just a homomorphism, we start with K as having the A as having the structure of a K vector space under multiplication. I mean, this is enough to give you. Yeah, but I don't even I drop the I. I don't even use the I. That's not entirely true. But for example, in the world of representations of p-adic groups, we form there's this algebra. I don't know what other people call it. I call it the big Hecke algebra because there's way too many things called Hecke algebras. And this is just all locally constant, compactly supported functions on G. And this doesn't have an identity even. So it's a non-commutative, non-identity ring. But it is kind of important because you get information from, you take these representations and you take like traces of these acting on modules. And that's an important thing. Although, in practice, one often takes there's a system of idempotents, and so for each compact open, you take the characteristic function divided by the volume, and then if you take the you take the algebra where you put this convolution on either side, now this thing becomes an identity. And for example, when K is the Iwahori-Hecke algebra, or so when K is the Iwahori subgroup, you recover the so-called Iwahori-Hecke algebra. But there's still value. There's still value in this non-C, non-I Kring. Oh, my handwriting is, oh, yeah. Sorry, I forget that. Maybe I should make as handsome as my face is, maybe I should make it a little smaller for legibility purposes. Yeah. Okay. Anyways, yeah, so the question is, how do we build back the ring homomorphism? But I would just probably, if we just define F to be, I mean, A has an identity, so just define it to be this scalar multiple, right? And by the ring axioms, this should be homomorphism, and then you can prove that that's the homomorphism. You can prove this is a mutually inverse thing. That if you take this process we described above, like by definition, you recover the vector space. I might put a poll soon. I know I talked about maybe we could do a group research project. I don't even know what we would try, but I'm thinking something. Try a group research project. Yeah, I have ideas. Maybe that's all the more reason to start a Discord server. But then I wouldn't want to put that behind the Patreon if that was like a thing, because what am I going to do? Be like, oh, pay me like $1 a month to be part of this research group? Actually, maybe that's not crazy if I made it inexpensive. Yeah, well, fair. But now you see. Maybe a learning seminar sequence first? Maybe. Why would the locally constant, compactly supported smooth functions on G be non-commutative? That is a commutative ring by pointwise multiplication. But we are not using pointwise multiplication. We're using convolution. So our product is phi convolved with psi, which is the integral over, I always get which side the inverses go on wrong, but something like this, roughly. I mean, partly because, for example, like, if you think about the finite groups case, where you have the equivalence between the representations of G and modules over the ring CG. What is multiplication in this ring? Well, if you view it as formal sums of elements, you know, formal sums of elements, the product, you define it to just be, now it becomes this double sum where you take the products of these elements. But in fact, the more rigorous way to say what CG is, instead of talking about these formal sums, is you say, well, it's the collection of all functions from G to C, and the element G can be represented as the indicator function of the singleton set G, and then actually if you unpack this multiplication rule, you find that actually it works out to be convolution. Of course, in the finite groups case, this is a sum instead of an integral. But yeah, it's kind of all the same. It's kind of all the same convolution. Yeah, I mean, technically, like polynomial multiplication is convolution as well. BT dubs. If G is connected and non-compact, that algebra is trivial. Well, I'm talking about, I'm talking about p-adic groups, which are totally disconnected. So it's definitely not compact, but very not connected either. And in this case, smooth, I write C infinity, but smooth actually means locally constant. So in that case, this algebra is extremely non-trivial. But one thing I was thinking of too, that's maybe keeps things in line with my research interest. We could do, I could start a new saga. Well, I do need to do spectral sequences at some point. I did think it could be fun to go through Getz and Hahn. Yeah. P-adic groups can be compact. Yes, that's true. But definitely not connected. Yes. I mean, they can be compact, but normally, like I'm thinking about things like GLN-QP and other matrix groups taking the QP points. Yeah. What nice analytical topological properties p-adic groups have? Well, I mean, all of your integrals are finite sums secretly of smooth functions. So that's nice because a lot of yucky topological considerations, that make integrals maybe more difficult in the Archimedean setting. Become easier. You wasted 10 hours trying to prove that if L over QP is degree n, ramification index E. Okay, so L over QP is degree n. The ramification index is E. And the residue field of F is order. And so let F be residue order, which is n over E. Oh, then the residue order is n over E. Never finished the proof. So in other words, I mean, it's the general statement that for any p-adic field that this is true. Right? Can I do the proof from memory? I mean, we just have one prime, right? There's only one prime, and it should probably mimic the case of global fields, right? So we have our ring of integers over ZP, and our prime ideal is sorry, my brain just stopped working for a second and decided to make a song about it. Right, this is gonna be this should be var pi E O L, right? We just have this choice of uniformizer. Yeah, the thing you're trying to prove is n equals EF, but every book either takes this for granted or uses something stronger in the case of Lang and Neukirch. That skips steps and looks like nonsense. What, this statement? Okay. So let's go back and prove that then. Singularity asks, though, if G is non-abelian, convolution is non-commutative. How does that non-commutativity manifest in the structure of CG modules? I mean, I'm not sure what to say there because, in some sense, because, we have this equivalence of categories, it's kind of like the same thing as just saying, well, how does the non-commutativity of G manifest in the category rep G? And, well, as you might know, if G is abelian, all the irreducibles are one-dimensional. And if not, then you have some higher dimensional E-reps, for example. So, by virtue of that fact, that same thing manifests in the category of CG modules. So I guess you just have more complicated irreducibles. That would be one thing to say, I suppose. Almost every single book skips steps in the proofs. Yeah. What are some cool properties or facts about CP that are beginner friendly that I know? You're supposed to present something on p-adic numbers tomorrow, and it's 99% done, but you need to say something about CP. Yeah. Off the top of my head, I don't know. I would just search a random PDF, but I mean, it is as a field, it is isomorphic to the complex numbers, but not continuously. Obviously, it's not isomorphic as a topological field. But of course, this depends on the axiom of choice, which tells you that all uncountable fields are entirely determined by their characteristic and their cardinality, algebraically. So, yeah, that's a fun fact. I mean, it's I mean, by definition, or I guess not quite by definition. I guess you kind of need to prove something, but you know, as you probably know, it is both algebraically and analytically complete. So that's cool. Yeah. Well, okay, let me ask you this though. Maybe that CP is algebraically closed, even though it appears as a completion of QP bar. Yeah. I mean, that is a theorem. Characteristic and cardinality, that would work for R and C though. Sorry. Also algebraically closed. Yes, sorry, we need algebraic closure as well. Yes, yeah, thanks for pointing that out. Yeah, that's very important. Yeah. But new wave infantry, to go back to your previous question, I mean, are you familiar at least with like var pi? So are like, because like OL is defined to be, you know, well, there's various different ways to define it, but you could define it to be like the closed one ball under the once you extend the p-adic absolute value. Like, are you happy with the fact that there is a uniformizer that generates the maximal ideal? Have you seen this? Because, for example, in Milne, you can look, I think, in Milne's algebraic number theory notes, like he sets you up to do all these things. Which, by the way, the full-on proof might actually be in Milne. Full-on proof might actually be in Milne, because once you get to here, once you get to this statement, yes, you know that we can split L by the powers of the uniformizer and the coefficients in there. Okay. But this statement you're still unhappy with, that this should be a power of this. So actually, yeah, let me think how to prove this. Well, I mean, I guess the thing to show is that this ideal is still prime, right? And then we know the proof is easier if you assume that you can take a uniformizer that is also a primitive element, but you haven't proven that except for totally ramified extensions. Yeah, I guess the tricky thing here is now, as I'm thinking about it, I'm like, well, which facts can I use and which facts can't I use? So I'm not sure what is in your toolkit and what isn't. Let's go look at Milne. Don't try to prove it here. It's surprisingly hard. Well, don't tell me what to do. I'll prove it if I want to. Yeah, let's see. Let's see. There should be a section on extensions, right? Rings of integers. Wait, absolute value is local field. Sorry, we want to be in here. What's the right section? Oh, extensions. Extensions of non-Archimedean absolute values. Is this what we want? Here's a corollary. It's right here. Corollary 7.4.2. Yeah. Actually, yeah. I wonder. Oh, you can actually use. So I'm not sure if this is what he's referring to, but actually, yeah. I guess the other thing. Maybe this isn't the easiest way to prove it, but the other way to do it would maybe be to, if you believe in that this is true in the global setting. I mean, either way, yeah, I guess there's more work that you need to do, because if you believe it's true in the global setting, then you could. I mean, I guess the one maybe not obvious step in the middle is that you could argue that any extension arises as the completion of some global extension. And then if you argue this, then the local one would fall out of that. I'm guessing that's how Milne is thinking about it. Yeah, because I'm sure that's what he's saying here in the global case, right? So 3.34, that must be right. Dedekind domains factorization. Yeah, he must be talking about the global case. Yeah. And let's see, this is a corollary to the extension. If K is complete, L is a finite separable extension, then this extends uniquely to discrete absolute value. Yeah. Hello, Arad. I don't know what your what is referring to, New Wave Infantry. I'm not sure which part specifically was confusing. Arad, we solved the quaternion algebra problem, I think, at the beginning of this office hour, after waffling about it for like 40 minutes yesterday. You have the memory that if you take the quotient OL by P, then use induction on E to compute its cardinality in terms of O omega. Yeah. We could probably try that as well, Jose. Yeah. How does L being the completion of a global field help? Well, because as one would expect, we should have like compatibility of these conditions, right? So we have like N is the sum of EI over FI, right? And so if you take E over Q, let's say, then let's say P lies over P, then the E of the extension of this completion should just be E of this prime over this prime, and like same thing with like F. And I guess the degrees should be equal as well. But then, yeah, I guess, I don't know. I mean, maybe if this is a surprise to you, maybe you're not happy to just apply that in the proof because, you know, you need to go back and prove those results as well. So, yeah. Yeah, so I don't know what the quickest proof is. Yes, I also really like that as well, Arad. Yeah. Yeah, I also really like that. Although sometimes I've seen people use R instead of G, and well, that is in one sense subpar because they're not in alphabetical order. I also like pronouncing ERF. So, you know. You could also write it as ref, but ERF is obviously infinitely more fun to pronounce. So. Okay. Yeah. I'm wondering for a potential direction for us to go for maybe a group research project is I have this idea at the intersection of representation theory and graph theory. And I think it's a very silly idea. And I'm not sure how publish worthy it is. Sometimes I think it is publish worthy, and then other times I'm like, but you know, it's basically just permutation representations dressed up. But maybe if we work on it together, if I put this idea out there, and I hope no one just steals it, and if we work on it together, maybe we can have the first YouTube channel platformed archive preprint. If all characteristic zero continuum-sized algebraically closed fields are isomorphic, does that mean that QP bar is also isomorphic to CP and C? Yes. 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 Yep. And in fact, there are even, you know, papers that say something like, oh, choose an isomorphism of QP bar with C, and then blah, 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 and do some stuff. Absolutely, this happens. Of course, you can never write one down, but you can choose one abstractly. Yes, extremely non-canonically. as non-canonically as one can be. Yeah. If there's a measurement, a cohomology theory to measure the lack of canonicity, this would be the least, be an infimum among canonical things. So I don't know, there's a lot of things on my mind right now. Group research project, or do the spectral sequence things. I kind of want to look through this paper. We could also go through Getz and Hahn. I don't know. Maybe I can't write one down. I mean, describe it explicitly. But I am a choiceless fool. I will always be a... What's that song? I'm a fool for love or something. I'm a fool for choicelessness. Yeah. This Valentine's Day, I'm going to write a poem about not using the axiom of choice. That's my plan. This is a cool paper. Also, I was thinking about going through. I know these people, but I don't know this person. At least I've never spoken to them IRL, or at least online. But the others I know. And so this seems like a cool little paper here about unitary representations for p-adic groups. Today you learned your spectral sequence computation from the past couple of weeks had an error somewhere. Yeah, that's how it goes, doesn't it? Anywho, well, maybe I should get back to work, but I was thinking maybe tomorrow we could try reading through this paper, possibly try to understand it, try to do some examples, maybe work out some examples in the GL2 case, although they have an example at the end of this paper here. So we could also do a sanity check to work through that. There's this example here. Yeah. Hopefully tomorrow you'll get here from the beginning. Well, who knows what time I'll even be logging on. It could be 6:30. It could be 9:30. Actually, yeah. I mean, unlikely to be at those extreme ends of the boundary, but then again, who knows? Okay. Well, I will see all y'all tomorrow, or I won't. Who knows? I mean, I plan to be here, but will you all be here? Or will you be busy proving corollaries to this paper before me? Anyways.